time we have seen vector spaces, linear transformations. We have seen what is a basis, or rather before that we have seen what is linear independent, dependent. Then we have seen a basis. We have seen that what is finite dimensional and what is infinite dimensional. And having seen a basis, we have seen, so if V be a finite dimensional vector space, so this is a finite dimensional vector space. Dimension of V is n, and let's say this is a basis. We have seen that there is a map which we write as coordinates with respect to the basis B. So if I take an X, it takes to, say if this is so this means that X is nothing else but alpha 1 B1, alpha 2 B2, and this is so alpha 1, alpha 2, alpha n give us the unique representation of X in terms of the basis B. And this sets up a bijective linear transformation What does it mean? So firstly, it means you give me any n tuple from R, so any member from Rn, there exists one and only one vector x in V whose coordinates is that given one. And furthermore, it means to say that coordinate preserves addition and scalar multiplication. Okay? So it preserves addition and scalar multiplication. And this is the winning trick, because this is a very, very important linear transformation, a relabeling of, and we are going to use this again and again and again in our whole course. Okay? So the first one was about linear transform. So suppose we have V and W, dimension of V is n, this is its coordinates, this is its basis, W with the dimension of W is m, and these are a basis, and V to W we have a linear transformation. And then we know on the side of B we have coordinates with respect to B as a bijective linear transformation. On the side of W we have coordinates with respect to say A, and there is this. And then what I was saying is there exists a unique the unique part is written expressed by this exclamation. There exists a unique linear transformation F star from Rn to Rm, and what is it? Well, that was given by this. So suppose you look into this matrix. Nice. Please close your microphone. Well, if you look into this matrix, whose first column is the coordinates with respect to the basis in W of the image of the first element. The second column will be the image of the second one and its coordinates with respect to that, and so on, right? So there are n columns. Remember, these are all m vectors. So this matrix I denoted as matrix if I take this, so this is actually a m cross n ordered matrix. Okay? And what was F star? F star from Rn to Rm was given by, you take n tuple, you multiply it by this matrix. So that is your linear transformation. Okay? So, what is it saying? This diagram is this picture is very, very nice. It says if you start off with an X over here, you take its coordinates and if you apply F star over here, what is the result? There's another way to evaluate it. You first evaluate F and then you apply its coordinates. Okay? So that means this equation is telling you how to get the coordinates of fx with respect to here. Well, you multiply by this matrix the coordinates, the original coordinates of x. So that's why this is often called the change of, or rather the transformation matrix. These matrices are often called, therefore, transformation matrices. The name of this matrix is often transformation matrix. Such matrices. Because they are intimately, they allow you to compute the coordinates. Okay? So every linear transformation therefore can be looked upon via this matrix, right? This unique matrix, F star. So that provides us a beautiful geometrical picture of this kind of abstract thing. Okay? Alright. Now, as a special case of this, for this, what happens when we have V and W to be the same vector space, but we have two different bases? Okay? So, as a special case, so V is there, its dimension is n, and you have B and A are two bases of V. Okay? And what's the linear transformation that I am taking? I take the identity linear transformation. So remember, what is it? It doesn't change the identity. The same thing. Right? So, what would be? So we would like to find out the matrix. So initially on the domain side we had B, and the codomain we have A. So I am taking first B with basis B, and on the codomain side V with basis A. Okay? And I want to look into this. So by my formula, this is coordinates of A, of 1V of V1, and so on. This is coordinates of A, 1V of Vn. Okay? But 1V doesn't change anything, so this matrix is same as I am rewriting it. Coordinates of A of B1 the second column is coordinates of A of B2 and so on. Coordinates of A of Bn. So this is a n cross n matrix, right? So what is this? This is nothing else but the change of basis matrix. Okay? What happens if you change your base? How does your coordinates change? So this is written as, a short form of this is P from B to A, and this is called And the reason is obvious. If you take any x in V, so what's the coordinates with respect to A of x? You just multiply the coordinates of x with respect to B okay? B to A gives you A. Okay? Clear? So, that's why this formula often tells you the name, why it is called the change of basis matrix. So you take the coordinates of x with respect to B, you want to get hold of the coordinates with respect to A, you multiply by the change of basis matrix. Okay? Clear? Alright. See, this formulation is very, very simple, provided you get this basic thing. This one is the starting point. Okay? Alright? So now let us see another thing. Remember, I shall denote it like this. This is the set. This is a standard notation. This is the set of all matrices. With real entries. And order okay, all n cross n matrices with real entries. That set is denoted by this symbol. Okay? GL stands for general linear. We will see later on, we will see why it's this called so. And similarly, if we have just a single one, this is the set of all matrices, square matrices. Of order n with real entries. Now, you have two m cross n matrices can be added. You know how to add them. Okay? You know how to scale and multiply matrices. So you know okay? This is a vector space. Alright? Because you know how to add them under the usual addition and scalar multiplication of matrices. Okay? Alright? Now, you also know about multiplication of matrices, but there is m cross n has to be multiplied with an n cross p. Alright? So, you have something like this. It's not an operation, but it can be looked upon as a function. So it's an m cross n matrices and n cross p matrices, and it is going to n cross p matrices, right? So that matrix operation I'm just writing as so if you have a pair like this is a Cartesian product of two sets, so its members are pairs. A coming from this means it's an m cross n matrix. B coming from this means it's an n cross p matrix. I can multiply them to get hold of an n cross p matrix, right? Okay. Similarly, okay. So and this multiplication has some, we know this multiplication whenever these additions are defined. That means we know for m cross n matrices A and B and n cross p matrices, we know that A times B plus D, that is equal to AB plus AD, as well as A plus C times B. This is AB plus CB, lambda A times B, this is lambda times AB, and this is same as A times lambda B, right? These are all peculiar things that we know about. So this is nothing new. This is all that you know about matrix addition and matrix multiplication, but phrased in this new language of sets and functions, right? Well, you cannot have AC because both are m cross n order matrices, right? Clear? So, I didn't write anything new. This is actually nothing else but matrix operations written in this new language of sets and functions. Okay? Clear? Yes. Okay. Now what does this matrix presentation of a linear transformation tell us? Remember, we have also shown that on VW, so this is the set of all linear transformations, from V to W. We have already shown that this is a vector space with pointwise description of addition if f and g are in this, and lambda is a scalar, f plus lambda g, this is also a function from V to W. How is it defined? It takes x to fx plus lambda times gx. Please, the centers, close your microphones. Yeah? So with this it was a vector space, and we did it in one of our second lecture or so on. Third lecture we did it. Okay? Now just in parallel, let's suppose that we have another vector space P. So you are going to see something parallel. Okay? So these are things from V to W. So what does it look like? And these are things from W to P. Okay? So if I take a pair from here, so it looks like this. So it commutes, it composes, and it gives me a homomorphism. Okay? It gives me a homomorphism from V to P. Yeah? Which is the composite. Okay? I'm just describing a function, and I leave it to you to check. If then as well, okay, very similar to the matrix ones, but I ask you to check. But the real thump is going to come now. So what is it? Remember, this is a vector space, and so is all the M cross N. So I am taking dimension of V to be is the basis for, okay? remember, this was this map. Okay? So it takes a homomorphism from B to W to the matrix presenting that homomorphism. Remember what was it? This is nothing else but, it's very simple. You look into the coordinates with respect to A of FB1, coordinates with respect to A of Fn. So these are your columns, and that is that matrix. Right? Okay. Now, is this linear? Firstly, the fact that given any f there exists a unique such thing. Okay? So this fact, that diagram which I drew, right? That tells me, so if I start off with a matrix, so suppose A is okay? Now I'm going to give you a linear transformation whose matrix will be this. Okay? How do I do it? So, I define FB1. So I define the coordinates of FB1 to be the first column. Okay? The first column of this. That means this one. A11, A21. Okay? And so on. That is the nth column. How do I get hold? Let me take any x from V. I look into its coordinates. Remember, this means that x is alpha 1, b1, alpha 2, b2, and so on, right? And I so hence put I leave it to you to show that check A's. And okay? So what does this show? I defined a function, and in the first part I took any matrix, so something from the codomain. I exhibited an F whose matrix is this. That means this function is actually surjective. Okay? So the function above, why don't I give a name to this function as the matrix representation from B to A. Okay? So, that's a surjective function. Okay? And the fact that it is the unique one tells me it is bijective. Okay? So it's a bijective function. So you see, the notion of a bijection was a relabeling. Okay? So over here, just as coordinatization relabels the vectors as members of Rn, matrix presentation relabels your linear transformations as matrices. Okay? So now let's see, the next part. Is this linear? So, let me take it's trivial now from so matrix so what is it? This is coordinates respect to A of S plus lambda G at B1. Right? And so on. That's the definition. Now let me use the definition of S plus lambda G. So this is that's the definition of S plus lambda G. Now use the fact that coordinatization is a linear map. So therefore, it is nothing else. So the first column looks like and so on. The last column looks like now, so you see each of the rows, each of the columns of this matrix breaks up therefore. So I can write this as this matrix plus But the first one is nothing else but matrix from B to A of F plus lambda times okay. So what's the result? Matrix turns out to be a linear transformation. So it's not only it's a linear transformation as a bijection, okay? So you see how the geometry sweetly flows in now. Using coordinatization and matrices, the geometry is sweetly coming in. Okay? So we have two things. These are this is actually the translation between our, you might call, abstract vector spaces and linear transformations, and the concrete RNs and matrices. So what is it? So summarizing, so we have, for a finite dimensional vector space, we were having this on one hand. Remember this diagram. F star is multiplication by the matrix, and okay? So this is also a bijection, and this is also a bijection. So these are two relabelings that is going to help us throughout next in our course. Okay, so every matrix is a linear transformation from, it's an m cross n matrix, so then it is from Rn to Rm, from an n-dimensional vector space to an m-dimensional vector space. Okay? And yes?
Did you say that every linear transformation is a matrix transformation?
Every linear transformation is represented by its matrix, which is obviously a matrix transformation, which is a transformation matrix, as we saw.
Okay.
Okay?
Thank you.
Yeah. So, matrix transformations and linear transformations are nonetheless the same thing. Okay? Under this bijection. Okay? So, this is what is going to come in handy for us. Okay? Little more. What was this? This was possibly T, right? Since I spoke about this multiplication and so on. So, let us take Rn and Rn. So that means hom VV So this linear transformations from V to V itself. Okay? No, wait. Before I do that, I can have another proposition. So just VWP are 3 vector spaces. Okay? And we have this friend here. So, where it is going, matrix does wonders even. So, where it is going from, so this is N, so let's put it to be P. Yes, there is a little bit of a reversal here. So that's how we define things. So what am I doing is dimension of V is N with a basis B, say. Dimension of W is M with a basis script A, and dimension of P is P with a basis script B. Okay? So this GF, remember what is this? This means V to W I have F, and W to P I have G, so I have the composite over here. Okay? So this GF goes to the matrix of this, and right? Now my question is, what is the matrix from V to P of G composed F? Okay? That is my question. Alright? So, I'll give you a hint, but I'll leave it to you. This is what this should be. What should this be? B is n-dimensional, so this G composed F is from n-dimensional to p-dimensional, so this should be a P cross n-dimensional matrix. Okay? Remember, this is what? From an n-dimensional to m-dimensional. This is an n cross n-dimensional matrix. This is from an n-dimensional to a p-dimensional. So this is a p cross m-dimensional matrix. Okay? In fact, what happens is, this is nothing else but okay? So see, there's a very nice connection. Matrix from B to P. How do I get it? B to A followed by A to P. Okay? This is just because of the reversal in how we write G cross F. That's why this reversal. So B to A and then A to P. Okay? So I leave it to you to check this. Okay, how do you check this? So I'll just give a hint. So matrix from B to P, G composed, what should it be? So its columns are G composed F of coordinates in P of G composed F of B1 coordinates in P of G composed F of Bn. Okay? That's it. Let's try with this. So what is coordinates in P of G composed F of B1? So what is this? This is coordinates in B of G of F of B1. Okay? Now you have to use this judiciously. The first thing that I did about this formula. How do you compute the coordinates of the codomain with respect to the basis in the codomain of f of x of the image? Well, it is the transformation matrix B to A of f times the coordinates originally. Right? So new coordinates, you can read it like this. New coordinates is transformation matrix times the old coordinates. Yeah? So that's what we are going to use. Again and again and again. So that's what we are going to use here. So this is the new coordinates. So this is matrix of this times the coordinates of A and F of B. Okay? This, again, this is what is this? Okay? Right? So, there is nothing special about B1. Is going to hold for each one of them. But what is coordinates of B1 with respect to B? The basis we remember. B1 is the first vector in the basis B. So what is this? So what is this one equal to? How can you write B1 in terms of, remember your base is B, you're forgetting what do you mean by coordinates. Coordinates, yes?
I'm going to use the formula that you showed us right now.
Which for, that formula was for new and old.
Oh.
Right? But so I'm asking, what is the old coordinates of B1? So here again you have to remember what is coordinates of something. Well, coordinates of x is the unique way in which you can write x in terms of the basis vectors of B. Right? If x is alpha 1, b1 plus alpha 2, b2 plus up to alpha n bn, coordinates of x with respect to b is alpha 1, alpha 2, alpha n. Okay? So how can you write b1 in terms of b1, b2, bn? Still not clear? Come on. The reason is you have a block with these letters. You are not making these letters friends. What is the best way? This is a vector. So b1 is obviously equal to b1, 0 times b2. You can write it in this way, obviously. 1 times b1 is b1. Right? And this is the unique one because it's the basis. Right? So, coordinates of b1 is nothing else but is there 1, 0, 0. Okay? So what is the coordinates of B3 say? And the rest are 0. 1 in the third coordinate and the rest are zeros. Okay? So you see now, this matrix, how is it looking like? This matrix times this matrix times this is the first coordinate, first column. For the second one, B2, second column. Okay? But now if you write coordinates of B1, B2, Bn, that is going to give you the identity matrix. Right? So therefore, this matrix turns out to be this. Okay? So that's the proof. See? In your book, possibly you wrote out several equations, substituted them. That's nonsense. You don't need it. Everything is built into the structure. What is the structure? Coordinatization and matrices. This is linear. This is linear. Okay? So, matrix coordinatization is linear. So, what did we do? We showed, so this is a linear bijection. This is also a linear bijection, but it has another beautiful property. I cannot say that it preserves products because this doesn't have any products at all. Okay? Cannot multiply two things here, but some such thing. So, it transforms the composition of linear transformations into matrix multiplication. Right? So, matrix transforms composites into multiplications. Okay? So, everything is now getting transformed in terms of matrices. So, this transforms composites to matrix multiplications. That is what the formula is telling us. What is the matrix of composite? It is the product of those individual ones. Okay? That's what it's telling us. Okay. So, now, let us look into home PB. Hom BV is a vector space. Okay? And now, since these are all linear transformations from V to V, I can compose any two. Right? And the squared matrices on R, I can add them and I can multiply them. Okay? So matrix in this case is a much well-behaved map. This map can take B to A. Okay, B and A are two bases. Okay, this is much more now. This map preserves addition, scalar multiplication, and composition. Remembering that composition is transformed into matrix multiplication. Yes? And we are going to use this. So see, just an aside, what is the difference between the operations on a square matrix? The difference is a little bit subtle. It's almost like numbers, right? We can add, we can scalar multiply, we can multiply. The multiplication distributes over addition from both sides, right? Now, A times B plus C is AB plus AC, and same as B plus C times A is BA plus C. Okay? It distributes from both sides. The only difference is, with numbers, the multiplication is commutative. Right? With matrices, it is not commutative. Okay?
Do we sometimes get can you get some? Do you sometimes get the one that we communicate here when we multiply the matrices?
Yes, sometimes. Sometimes matrices multiply in a commutative way. We are going to show that. Yes, sometimes, but not always. It is not true that all matrix multiplications are commutative. Okay? Clear? Alright. So it's very much like numbers, and we will see there is a big thing that I told you about. Now let's look into another aspect of linear transformations, which coordinatization gives us. And that is possibly number 4, building that is our how to build, how to give examples of linear transformations. So you assume that the domain is finite dimensional. Assume make a set, and let me take B to be this. How many elements does the set B have? N. And you are very happy to describe functions in finite sets, right? A 20 element set, you can describe. You have no problems with that. Good. So, B is obviously a subset of G, right? Okay? So remember, for any subset I say that there is a peculiar function called the inclusion map, which takes the elements to itself, right? So you have already this inclusion map.
Professor?
Yes?
Can I ask? I don't know if you can clarify and understand the strategy before we the subset.
Yes.
The subset time. We are using ambiguity or using because in understanding of the time, it is proper or
I'm using it. In general, it will be proper because V being a vector space will have infinitely many elements. Okay? And B has finitely many elements, so it is proper. But I use this notation A is a subset of B in this ambiguous sense. It is proper or equal. When I want to say it's proper, I'll specify it by writing a not equals to below. Okay?
Because I'm just confused as well.
Yeah, okay. For me, I will, for proper and not equal to, I will specify it like this. Okay?
Thank you, sir.
Okay. So, remember this function which takes x to x itself. So that means it is an inclusion map. Okay? Alright? So B1 is going to B1, B2 is going to B2, and so on, right? So I have this. And your W is any vector space. Okay? V is finite dimensional given, and I give you any vector space and a function. F is a function. Okay? You told me just now, giving a function from a set, from a finite set in particular, is not difficult, right? You just tell me, therefore, n vectors, FB1, FB2, right? Clear? So, let you are given. Now, with just this information, I'm telling you, it's enough. I can create a linear transformation. So I'm saying that then there exists a unique, This is the statement. So this is all that is given to me then. There exists a unique linear transformation such that F bar So what does this mean? There exists a unique linear transformation here. And see, what does this mean? So what is F bar composed iota B? This is, I'm saying, equal to F. That's exactly the n equations. Why? Iota B is defined on B1. Iota B of B1 is B1, so that is F bar of B1 is F B1, which is W1. F bar of B2 is W2, and so on, right? So that's actually saying this one computes. Okay. Now, what is the definition of this F bar? There's only one way you can do it. If F bar has to be linear, there is only one way you can do it. No two ways. F bar has to be linear. So, what's the proof? Suppose you take x from V. And, well, suppose coordinates of V of x okay? So you define F bar of x to be alpha 1 W1, alpha 2 W2, and I leave it to you to show that this F bar is a linear transformation. See what I have done. F bar of alpha 1 B1 plus alpha 2 B2 up to plus alpha n Bn is actually, I am saying, alpha 1, what is W1? F of B1. But what is B1? The coordinates is 1, 0, 0. Right? So by this description, F bar of B1 is W1. Right? So, alpha 1 times F bar of B1, alpha 2 times F bar of B2, and so on. That's what I do. So this F bar, as you can see, so as if, what did I do over here? If you can visualize it, if you can try to visualize this picture, what was it? So, the picture is like this. You have this big vector space V, and you have this one W. Okay? And you have a very small little subspace here. Rather, not a subspace, but a subset here. Very, which is the basis. But this is very strong. In what sense? If you give me any function from here to here, okay, this function extends to a linear function from here to here. Okay? So this extends to all of you. You're just given me on this little subset, right? But it extends now to all of you. Okay? So it's something rare, right? Trying to restrict functions is something simpler, but trying to extend it is a tough task. Okay? But that is nature. And that is because B is a basis. Because B is a basis, and every element of V has a unique representation in terms of the elements of B, in terms of the basis. Use that unique representation to make this extension possible. Okay? So this is one side of the story, this pictorial side. But what is it also telling us? It is telling us ways to create linear transformations whose domain is finite dimension. I don't bother about, I didn't say anything about W other than the fact that it is a vector space. It could be infinite dimensional also. Right? But if the domain is finite dimensional, that's what. That is my picture. Then creating linear transformations with domain V is very simple. How? Well, I choose a basis. I say where does the first vector of the basis go? W1. Where does the second vector go? W2. Okay? So I choose a point n tuple from W. If the domain is n-dimensional, I choose an n tuple in W. Right? Choosing this n tuple in W is enough. I know by choosing that, this principle tells me how can I extend it to a linear transformation. Again, a unique one. So, the linear transformations from V to W is in one-to-one correspondence, you can see therefore, with choices of n tuples from W. However you might choose it, you get a linear transformation. A unique one. Okay? So, same as choosing n tuples. It is not very fascinating how to create linear transformations. Choose an n tuple, where n is this dimension of the domain. Okay? Choose an n tuple and you get a linear transformation. And this is the formula for creating that link. Okay? What does that n tuple do? The first one goes to the first one. Second one, back to the second one, right? And then you know how to extend it to. So this is often called the principle of linear extension. Okay? It's often called the principle of linear extension. The crux of the matter lies in the fact that B is a basis. If B was not a basis in the self-assessment equation, so you see, if B is not a basis, you may have a function which extends, you may not have a function which extends. Depends on the choice of your input. Okay? Alright? Okay. Now, there are many things coming out from this nice little machinery of coordinatization and matrices and so on. The next one. Do you agree that you can have is it possible to have an infinite dimensional vector space, a subspace of a finite dimensional one? No. Right? So, every subspace of a finite dimensional vector space is finite dimensional. Right? And just now, what we saw was any n-dimensional vector space under coordinatization is isomorphic with Rn. Right? So, if you have a 20-dimensional vector space, we know therefore what are its subspaces. It can be one-dimensional, that means R1, two-dimensional, that means R2, three-dimensional, that means R3, and so on up to R3. But there could be several R1s. You know pretty well, R2, each line passing through the origin is a one-dimensional subspace of R2, right? So there could be several such, but your subspaces could be either one-dimensional or two-dimensional up to n dimensions. Okay? Clear? What does this tell us? So if you have a subspace, if you have a basis for that subspace, you can extend it to a basis of the whole space. Okay? So that's the next story.